Hi. In this video, we're just doing one section out of Shankar, but there's two important topics, and we'll do one example from each. So the example shown is from the first topic, just the general position vector R, and notice how it's boldface over here in the book. So we're talking about position in more than one dimension. And then we'll also do an example on a related topic, relative motion. So that's down here in the book. Okay, so recall from last time, the video on vectors. We could talk about the position in the xy plane by the x coordinate and the y coordinate. And then, oops. So the I and j are basis vectors specifying the coordinate system. So for the normal xy plane, the I hat is pointing to the right and the j hat is pointing up. So x will just be some number, positive or negative, that says how much to the right or to the left you are relative to the origin, and y is the position along that vertical direction. So in this section, we want to emphasize the fact that this position can change over time. So if we're describing the position of a particle, that particle doesn't have to stay put. And so both the x and the y pieces can change over time. But in a Cartesian coordinate system, the basis vectors don't change over time. So notice how I and j hat are not a function of time. So you're used to a Cartesian coordinate system where the basis vectors don't change in time. Later in this course, we are going to see another polar coordinate system where the basis vectors do change over time. So there we're going to have to be a little bit more careful about this. But right now it's pretty easy. It's just the x and the y pieces depend on time. So you can probably guess what the velocity vector, how we're going to define it. So the velocity is how the position is changing over time. So it's the derivative of the position vector over time. And this is pretty straightforward, right? If you're taking a derivative with respect to time, you can take a derivative of each piece separately. So this is dx dt in the I hat direction and dy dt in the j hat direction. So visually, I think this is kind of clear. So r hat points in some direction, and then after a small amount of time, the position will be somewhere else. So the position is labeled by r plus delta r. And so delta r is the final minus the initial, but as a vector this time. So maybe the x piece changed by some amount and the y piece changed by some amount. And that's specified by the two vector components of delta r. So delta x and then I hat makes it a vector component rather than just a component. So the particle will trace out some path in the xy plane, and the velocity is going to be tangent to that path, right? It's just the direction the particle is moving. And the faster the particle is moving, the bigger the magnitude of this velocity vector is. So, whoa, that is not the direction we want to go. So acceleration is just another derivative, right? So this also generalizes pretty easily for another derivative. This is a derivative of the velocity vector with respect to time. So dv. So now we have to talk about, we can't just say dv. We have to specify the x component of the velocity. So dvx dt, and then dvy dt. Oops. In the j hat direction. So this thing, dvx dt, this will be the x component of the acceleration. And this thing right here will be the y component of the acceleration. Okay. You could also think of x as r. So r sub x is the same thing as the x coordinate, and r sub y is the y coordinate. So we're using r now just to emphasize the fact that it's more than one dimension. But other books, you might see an x with a vector sign on top. So that just means it's the same thing as r, and they're trusting that you won't get confused that x doesn't just mean the x coordinate, it means all of the however many dimensions you're working in. So if there's two dimensions, the x vector will have two pieces, x1 and x2. So they might use numbers rather than different letters for it. It's just so it's easy to generalize to more dimensions. Okay, so I think we're prepared. So taking derivatives is easy. This example is going to have us go the other way and find integrals, which is just a little bit more tricky because you have to be careful about the constant of integration. All right. So looking at this example, a particle starts off at 6, x equals 6 and y equals 8. And it's moving with some speed. And by the way, these are meters. So we're being a little sloppy with the units. It will just be understood that x equals 6 means x equals 6 meters, and y equals 8 means y equals 8 meters. So, if we wanted to be careful with the units, we would write it in like that. Okay, so we're given an initial velocity of the particle, and we're given an acceleration of the particle, which depends on time. So this is, so I want to emphasize that this depends on time. So we won't be able to use equations for constant acceleration, like the equations that we derived towards the end of chapter 1, and equations that we're going to revisit for projectile motion. We can't use those equations because those assume that acceleration is constant. Acceleration is not constant here, so we can't do that. So we have to use the full general equations for motion here. Okay, so to find so we have the acceleration as the exact function of time. We don't know the velocity as a function of time, but we do know the acceleration as a function of time. So we know the acceleration at all times. And so since we know everything about acceleration, let's start there and work our way up towards the position. So we'll have to go from acceleration to velocity and then to position as a function of time. And that'll help us answer the question. Okay, so the original problem we're doing now. So the original problem has the acceleration was it minus t in the y-hat direction. So we can integrate this to find the velocity. So by the way, I'm gonna write plus 0 in the x-hat direction. I can always add 0. So the velocity is the integral of a of t dt. So for Cartesian coordinate system, this is pretty easy. You just have to integrate the separate components. So we can just do the integral of minus t dt in the y-hat direction. And then in the x-hat direction, it's going to be integral of 0 dt in the x-hat direction. So you'll get a constant of integration for each of these. So the only thing we have to evaluate here, it looks like it's this one, the minus t. So this is minus 1/2 t squared. So I wrote this as an indefinite integral. So the velocity as a function of time is this plus a constant vector. So I could write constant vector right here, but that vector is going to be a special thing. That's if we plug in t equals 0, and we plug in t equals 0 right here, this term goes away. What that constant vector is it's the velocity when t equals 0. So because of that, we can just, instead of writing c, we can be a little bit more specific and say that it's going to be the initial velocity vector. Right? So it's going to be the velocity when t equals 0. And we know this from the problem statement. So this is what we're given. We are given v naught is minus 2. That's that constant initial velocity vector. So we're given in the problem statement that v naught is minus 2 meters per second. Or, remember, we're assuming SI units. We're already sloppy right here, right? Second squared is not the same thing as meters per second. So that minus 1/2 really carries with it units. Meters per second. No. Meters per second cubed, because when you multiply by second squared, you get meters per second. So we're given that this is true. So right now this is bad because I have a vector on the left-hand side and a scalar on the right-hand side. So we definitely have to make sure that we specify the direction right here. And remember, it was in the minus x-hat direction, minus 2x-hat. Okay, so now we have vector equals a vector. So every time you write down an equation, you have to make sure, am I saying a vector equals a vector, or am I saying a scalar equals a scalar? And so you may have noticed, you may have complained already, Well, this piece right here looks like I have vector equals scalar plus vector. That's no good. They all have to be vectors. And so really, I made a mistake right here, right? Looks like this piece, I forgot the y hat right here. So it's this in the y hat direction. Okay, so overall, putting these pieces together, so filling in this for V naught, we have the velocity as a function of time is minus 2 x hat plus negative 1/2 t squared y hat direction. Okay. So now we know the speed of the velocity of the particle at all times, not just at t equals 0. At t equals 0, it was minus 2. But now we know it at other times. So it's going to pick up speed in the negative y direction. It starts off going this way, and it looks like the x piece is always this amount, but it's going to start to gain speed in the y direction. So, sorry, gain a y component of velocity. So it points down a little bit, points down a lot for the vertical vector component. And then the horizontal piece is always minus 2. Okay. So the path of the particle is going to look like this. Does it bend a little bit? Does it bend a lot? That's what the problem is asking for. Where does the particle cross the y-axis? So we're not quite done. We have to know where it is at all times, right? So let's keep going. So we want the position vector now. So the position vector is going to be the integral of the velocity vector. So we can integrate each term and then just remember that we need a constant of integration. So this is going to be minus 2t x hat. So I'm just integrating this piece with respect to time. And then the integral of t squared is 1/3 t cubed. So we get a minus 1/6. Remember, there's still the minus 1/2. T cubed y hat. And we still can have a constant of integration for each of those pieces. So it's a constant vector of integration. And this is going to be the initial position of the particle. Right? Notice how if you plug in t equals 0, each of these terms is 0. So this is 0 if you plug in t equals 0. 0 when t equals 0. So the correct interpretation of that constant of integration is it's the position vector when t equals 0. Okay, so we're also given that. So we're given that x equals 6 and y equals 8. So we're given that the initial position vector is x equals 6 and y equals 8. That's so this initial position vector is this thing right here. It's pointing, this is the r0 vector. It's pointing from the origin to that spot, to that starting spot. And then as time goes on, you know, this particle is going to go maybe right here, then the position vector will point from the origin to that new spot. That's what r vector is. It's a vector from the origin pointing to wherever the particle is at that time. Okay, so overall, we have r as a function of time. I'll probably need some space here. R as a function of time is, gets to be pretty long, right? Minus 2t, and then plus the constant piece, plus 6 x hat, plus negative 1/6 t cubed, plus 8 in the y hat direction. Okay, we still haven't solved our problem, but this is going to tell us where the particle is at all times. So the problem should be pretty easy now that we know this, right? So the integration part is harder than derivatives just because you need to take into account constants of integration, which have some interpretation in physics now. All right, so let's see what the problem's asking. When and where does the particle cross the y-axis? So the y-axis is here. So what defines the y-axis? Well, that's when x equals 0, right? So we have to find out, when does x equal 0? When does the particle have x equals 0? So the problem is asking when does x equal 0? So remember what x is. It's the thing multiplying the x component. Notice how I kind of switched from I hat to x hat. Sorry about that. Just kind of use them interchangeably. But this is the x coordinate, negative 2t plus 6. So when does x equal 0? It looks like we have to set negative 2t plus 6. So it happens when at t, where t satisfies this equation, negative 2t plus 6 equals 0. So it looks like it happens at t equals 3. 3 seconds if everything's in SI units. So that's when x equals 0, and the question is asking, what's the y coordinate? You know, where is it going to cross the y-axis? So if we plug in, so y at t equals 3 is negative 1/6 times 3 cubed plus 8. And notice how this side is not a vector. It's just the y component. So I don't need a vector on this side right here. So 3 cubed is 27. Divided by 6 is 4.5. Is that right? 4.5 plus 8 looks like it's 3.5. So the answer is that the particle crosses the y-axis at position 0, 3.5 when t equals 3 seconds. That's our overall final answer. So it looks like, 0, 3.5, it looks like, so if we were to track the trajectory here, looks like this particle crosses about right here. So it looks like maybe this is the path of the particle. We could also figure out where it crosses the x-axis. It should be, looks like it happens at some negative x coordinate, right? This is the direction that the particle is going. So because the acceleration is gaining over time, this is actually not even a parabola, it's a section of a cubic equation, right? This is, remember that r is a function of time, has this t cubed. So it's going to be a little bit steeper than a parabola. Okay. All right, good. Now the next thing your book does is it talks about, okay, so it says that you can have a position vector, and then just using vector addition, you can chain together these position vectors, right? So the example in the book is the plane relative to the ground. So this RPG right here, RPG is the plane relative to the ground. And then it's tracking, so I guess the back of the plane is the position of the airplane, just to be exact about it. And then they're talking about a ball on the plane, in the plane, which can be at a different spot in the plane. So our ball relative to plane. So where the ball is relative to the ground, it looks like it's just the vector addition of these two, right? The plane relative to the ground and then the ball relative to the plane. And when you add those two, you get the ball relative to the ground. So that's true for the position vectors. And then you can take a derivative to get that this is also what's true for the velocity vectors and the acceleration vectors as well. So this topic that we're going to talk about of relative motion focuses on the velocity part of this. The accelerations is also a interesting thing, and we're going to talk about inertial frames and all that with Newton's laws. And your book alludes to, this has something to do with the relativity too. So we'll hold off on 2.45. 2.44, relative motion. The velocity of A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C. Now it doesn't matter what the three labels you have here. The order is somewhat important here. Notice the center labels are so the way I remember this is that the center ones are kind of canceling out. So AB, BC, the B's will cancel out, and overall we're left with A and C. This is how I remember the order of these things. So I can, even though we don't have a quantitative example, I can give a qualitative one. So suppose you have and by the way, you don't have to use A, B, and C. You can use any other three things. Like your book did plane, ground, and ball. So we'll do an example where it's let's have a plane, and instead of a ball, let's have we're actually going to track the plane, not a ball. We'll track the plane. We're going to have some air, and then we'll also have the ground as well. Right. So if the air is moving to the right, so what do we mean by that? So I'm imagining this is a bird's eye view. I don't know if there are multiple birds or not. Birds, yeah, all of them view it this way. Bird's eye view. So this is the velocity of the air with respect to the ground. Right? When we say the air is moving to the right, we mean that relative to something, right? Relative to the Earth. So you might see Earth as well. So we could have done E for Earth. So the velocity of the air relative to the ground is to the right. And what that means is that you can't, if you were in an airplane, you couldn't just, and you wanted to go straight across, so straight north, let's say. Let's say the air relative to the ground is east, and then we wanted to fly straight north relative to the ground. You wouldn't just direct your plane this way because the air is going to make you drift to the right. Right? So you'd have to point your plane kind of this way, such that when you take into account the air moving relative to the ground, then you would be pointing straight up. Okay, so we want the combined effect of those two things to point straight up. So this is actually a vector equation. This is the velocity of the plane relative to the air. This is velocity of the plane relative to the air, plus the velocity of the air relative to the ground. That's this piece right here. Those two combine to give you the velocity of the plane relative to the ground. So if the goal is, for example, in this problem, so we said that maybe this we want to go straight north. So there should be no horizontal component to VPG. So if that's the case, we're going to point in whatever direction is required so that the horizontal component of our vector is going to exactly cancel out the air. Right? So a plane is probably going really fast, maybe 200 meters per second, 300 meters per second, and the air is only going 10 meters per second. So if this is 200 meters per second, this is 10 meters per second, you don't have to correct by much. But this will help you figure out exactly what angle you need to change your direction. So the plane needs to head a little bit due west of north, by some angle theta, such that when you take into account the air, you can be pointing just due north. Okay, so I don't think we need to go through a full example for you to get the gist of this. Yeah. So all right, that takes us to the end of this section.